So, continuing with our discussion of the topic of force and motion, we take a look at net force analysis. In the previous videos, we took a look at the types. We discussed Newton's laws of motion. We take a look at the types of forces that you are likely to encounter in this course. And we talked about equilibrium systems and accelerating system. Putting it all together, we take a look at how forces are analyzed. So again, putting things together, we look at how the net force analysis is done. When doing force analysis, and by force analysis, we typically mean net force analysis. When doing force analysis, follow these steps. First, take a look at the problem. The problem might provide you with a drawing or diagram of the system, or it might not. If the system does not provide a drawing or diagram, if the problem does not provide a drawing or diagram of the system, draw the system described or provided by the problem. So draw the system, and that will help you in the next step. Step 2, after you have drawn the system, identify the forces present in the system. Use the drawing of the system, whether it has been provided by the problem or you were the one who drew the system. So use the drawing to help you identify the forces. And once you have identified the forces, draw the free body diagram or diagrams, FBDs. Basically, a free body diagram is a vector diagram. Draw the forces and other relevant vectors that are present in the system. Some systems might have only one free diagram. Other systems might have 2 or more free body diagrams. Consider each object to have its own free body diagram. So if there's only one object in the system, then there's only one free body diagram for you to draw and analyze. If there are 2 objects in the system, then that means 2 sets of free body diagrams are needed. One free body diagram for object 1 and another free body diagram for object 2, and so on. And then the last step is analyze the free body diagrams that you have drawn using either F net is equal to 0, equilibrium system, or F net is equal to MA, accelerating system. F net, again, is summation of all the forces acting on the object. So, summation of the forces acting on the object is equal to 0, equilibrium system. Summation of the forces acting on the object equal to MA, accelerating system. Since you are doing summation of the forces, don't forget to use your component method when adding the forces together. Again, force being a vector quantity. It has both magnitude and direction. So consider the following example. Sample problem 1, and we'll do it step by step using the steps that we have just discussed. A string is tied to object A, to box A, and is passed over a frictionless pulley. box B is attached to the other end of the string, and as shown, the second object, box B, is suspended from the pulley as such. Box A has a mass of 2.5 kilograms. The static friction between box A and the tabletop is 0.75. What is the maximum mass that box B can have and still have the system in equilibrium state? So here, the problem has already provided a drawing of the system. So in terms of the first step, you can skip the first step because there's already a drawing of the system. But if not, then you have to draw the system. Let MA be mass of box A, 2.5 kilograms. Knowing mass, we can get the weight. Weight is vector weight. Vector W is equal to mg. Magnitude is equal to weight A is equal to MAG. So this is magnitude. It's just 2.5 kilograms multiplied by 9.8 meters per second squared. That will give you 24.5 newtons. You'll recall, if you know our discussion of weight in a previous video, if you know the mass of the object, you know the weight of the object, and if you know the weight of the object, you know the mass of the object. The coefficient of static friction between box A and the tabletop is mu s is equal to 0.75. No unit because this is coefficient of friction, unitless quantity. Step 2, identify the forces present in the system. Use the drawing of the system to help you identify the forces. So use the drawing to help you identify the forces. There's no applied force. Weight. As long as there is mass, there is weight. Object A has mass. Therefore, it has weight, and weight is always vertically downwards. You have weight A. Box B also has weight, also has mass. Therefore, it also has weight. If we can calculate or derive the weight of mass of box B, we'll be able to calculate the mass of box B. And that's what the problem is asking for. Next, because of its weight, mass A, box A is pressing into the tabletop. The tabletop will react by producing normal force, and normal force is always perpendicular to the surface. The surface is horizontal, therefore the normal force is vertical. Because of mass of B, because of the weight of B, B will be pulled downward. As such, the string will be pulled. The string will react to being stretched by producing tension. Tension is a pulling force. The string will pull at both ends. So it has an end here, so it will pull box A with tension T. And the other end is tied to box B, so it will pull box B with tension T. Now note, the pulley is frictionless. This means that it has no effect on the tension in the string other than redirecting the direction or orientation of the string. So there's only one tension in the string unaffected by the pulley other than redirecting the direction of the string. And because of tension T pulling at the box A, box A has a tendency to move to the right. So it has impending motion to the right. Static friction will arise to oppose that impending motion. Impending motion to the right. Static friction will be to the left, always parallel to the surface involved. Okay? We are looking for mass of B, maximum mass of B, and still have the system in equilibrium state. So the problem itself tells us that the system is in a state of equilibrium. The total acceleration of the system is equal to 0. The system is at rest, so this is static equilibrium. Now that we have identified the forces, and in doing so, we were able to draw the free body diagram. You have two objects, object 1, object 2. You have two free body diagrams. Free body diagram 1 on box A and free body diagram 2 on box B. So analyze the free body diagrams using either Fnet is equal to 0 or Fnet is equal to MA. The problem already tells us that the system is in equilibrium state, so we set Fnet to equal to 0. We analyze each free body diagram. Let's start with free body diagram 1, box A. So Fnet is equal to 0, equilibrium state. Fnet is summation of all the forces acting on the object. So you have weight, normal force, friction, and tension. So you get the sum of all of those forces, and they should be equal to 0. These are vector quantities, so we use component method. We have x component and y component. X component of Fnet is Fnet x. X component of 0 is still 0. Weight is vertical, no x component. Normal force is also vertical, so no x component. Friction, S, is horizontal, negative direction, so all of it is in the x component and heading negative direction, so negative Fs. Tension is horizontal, all of it is in the x component and it is heading in the positive direction, so plus T. The x component tells us, and it should be equal to, again, 0. The x component tells us that the magnitude of tension is just equal to the magnitude of the static friction. Going now to the y component, you have Fnet y component of Fnet, y component of 0 is still 0. Is equal to y component of weight. Weight is vertical, all of it is in the y component, heading in the negative y direction. So you have negative weight A. Normal force is also vertical, all of it is in the y component, heading in the positive direction, so plus N. Friction and tension are horizontal, no y component. Y component analysis tells us that the normal force magnitude is just equal to the weight A magnitude. And we know weight A to be 24.5 newtons. So that's it for the free body diagram 1. Moving now to the other free body diagram, FBD 2, box B. Fnet is equal to 0. Summation, Fnet is summation of the forces acting on box B. You have tension and weight. So, tension plus weight is equal to 0. Again, these are vector quantities, so we use component method. You have x component and you have y component. X component of F net is F net x. X component of 0 is 0. Looking at the diagram, all the forces are vertical, no x component. So we get no information in looking at the x component. Let's look now at the y component. Y component of F net y component of 0 is 0. Weight and tension are vertical, so all of them are in the y component. Weight is heading in the negative direction, downward. Tension is heading in the positive direction, so weight is negative, so minus WB, and tension is positive, so plus T. Tension, y component tells us that the tension magnitude is just equal to the magnitude of weight B, and weight B is just equal to mBg. We are looking for mass of block B, so isolate mass. M is equal to T over G. Maximum mass, we are looking for maximum mass and still have the system in equilibrium state. So, let's set M to maximum. So, you have MB max. G is constant. So, for M to be maximum, tension must be maximum. And in FBD1, we saw that tension is just equal to static friction, and we know that static friction ranges from 0 to a maximum value. So the maximum value of tension is the maximum value of static friction, mu s n, and we know n to be the weight magnitude of box A rather. So plotting this into the equation for MB max, you have MB max is equal to mu s weight A divided by G. Plotting in the values, we are able to calculate MB max to be 1.875 kilograms. So just follow these steps whenever you do force analysis. Again, draw the system if no drawing is provided by the problem. If there's already a drawing, you can skip step 1 and go to step 2. Step 2, identify the forces present in the system. And then, using the drawing of the system, draw the free body diagrams, FBD. Each object in the system will have its own free body diagram. And then analyze the free body diagram using either F net is equal to 0 or F net is equal to MA. And don't forget to use your component method because force is a vector quantity.